and don't bother writing this down, but because I'm going to erase it here. But if we had x cubed times sine x as a function and wanted to do the derivative, if I hadn't just told you that it doesn't work, what would you guess the derivative would be? Right? If things were really going to work nice for us, that would be true, and it's not. Okay? The derivative of x cubed sine x is not 3x squared times cosine x. We cannot do their individual derivatives. So when you realize that, it makes this first rule a little more important. It's like, oh, okay, it's nice when we add or subtract functions that we can then just take their individual derivatives. That's good. Because when it comes to multiply and divide, it doesn't. All right? Next thing, we talked about if you have a constant multiplied in front of a function and you want to do the derivative, what do you do with that constant? If you have 3 sine x, what's the derivative? No, don't confuse antiderivative. It's just 3 cosine x. Okay, here's an easy one. What if you have 3x squared? 6x. What'd you do with the 3? You just left it there. The 2 comes down in front, multiplies with the 3 because it's still there. So the lesson is, when we have a constant outside of a function, we just leave the constant there and we do the derivative like normal. So anytime there's a constant in front of a function of x, we just leave the constant there. Now, we did talk about that being a stretch. We said that's a vertical stretch, which is going to also make the slopes that much more, right? That's why we put it there. But that's our rule, okay? And then we also had this rule that if you have a constant multiplied inside the function, what are you going to do? What did we say? Remember, if you have sine 2x, what happens to that 2? It stays there and doesn't change, and remember kicking it out? We didn't do very many of these, okay? And that's why I didn't put them on the quiz. But we kick it out. So if you had sine 2x, well, we can try it on the calculator real quick. If I come on here and I go under the template bar here and grab derivative and put an x, I thought I showed you this. It's been a while ago, though. And I do sine 2x, and I tell it to do the derivative. There's a 2 on the inside, and it kicks out a 2. And so the rule is that we'll kick out the constant, and we'll do the derivative, and we'll leave the constant on the inside, too. Okay, so that was something that we've already talked about. We haven't done very much with it, but now we're going to do more with it. So one of the things we're going to do over the next 3 days or so, 3 or 4 class periods, is we're going to be doing some more of these derivative rule problems. Okay, and trying to get a little better at them. When we come back after Thanksgiving, that's all Chapter 3 is about, is derivative rule. Okay? All right, so we had those. Now we get into the other rules we've already talked about, and we already talked about e to the x. The derivative of e to the x is e to the x, right? Oh, shoot, I forgot the most famous rule of all. Let's squeeze that in now. I'm going to put it over here. What's the rule we're using the most? Power, right? X to the n power is n times x to the n minus 1. That's the rule we've really been using a lot. Power. Right. That, remember we talked about that? We graphed the e to the x graph, and we said its slopes are its y values. Its slopes are its y values. Now, what if it was e to the 2x? What if it was e to the 2x? You'd have to kick out a 2, right? I mean, don't write it down necessarily here, but if you were doing the derivative of e to the 2x, the rule of e to the x is, hey, it's its own derivative. It stays the same. So it would just stay the same, but we'd have to kick out a 2, right, because of that rule before. So what happens when we do these derivatives, we have to combine these rules together, right? So derivative e to the x, it's its own derivative. Nothing changes. Except now we also have the rule if there's a number in the middle, in the inside, we have to kick that out. Okay? So keep that in mind. All right. Now, here's a new one. Here's a new one. And this is what section 6 is about. What if you have some other base besides e? Okay? Now, keep in mind the power rule over there. Notice the difference here. Because this is one of the common mistakes people make in the beginning. Is they have e to the x and they want to bring the x down in front and then drop the power to x minus 1. No, the power rule is when you have x raised to a number. That's for power functions. X raised to a number. We use the power rule. A number raised to x is different. That's an exponential function. Those are two different things. It's kind of strange because I know in algebra when you learn about exponentials and powers, you use those two synonymously. An exponential, or excuse me, an exponent and a power is really the same thing. But as functions, they're two different things. An exponential function is a number raised to an x. A power function is an x raised to a number. Very different things. Derivatives are totally different. All right. So, here's the derivative on this. It's closely related. It's its same derivative. So I'm talking about 2 to the x, 3 to the x, 4 to the x, something like that. But you have to tack on the natural log of whatever the base is. So if the function was 2 to the x, it would be 2 to the x times ln 2. Now ln 2 is just a number, but that's what it would be. Now, you think about it, actually that fits here, right? This rule could apply here. Yeah, because you'd have e to the x times ln e. And what's ln e? 1. ln e is 1. So it would just kind of go away. So what, right? So this is really the generic rule for all exponentials, but this one's so important and we see it so often, we just kind of write it as a special rule. All right. 2 more that'll be in section 6. Section 6 is about exponential functions and log functions. So let's do our more famous and more popular and more the one we'll use the most, the natural log function. What's the derivative of the natural log function? Well, it turns out it's very simple. It's 1 over x. It's 1 over whatever's on the inside. So if we had ln of 2x, it would be 1 over 2x. And we'd have to kick out a 2. Right? Because using the previous rule. But whatever's on the inside of natural log, we do the derivative, we do 1 over that. Okay, now this is a strange one in the sense that it's the only one that doesn't stay within the same function family. When you do a trig function like sine, you get another trig function, cosine. When you do a power, you get another power. When you do an exponential, you get another exponential. But when you do natural log derivative, you get something that's not a log, right? You get 1 over x. Yes? Okay, so let's do an example. So let's say we had derivative of, well, here, let's just throw a couple out here. So let's say we had ln 2x plus 3. And we want to do the derivative of that. So what you do is here's how you use these rules. They're like a formula almost. So you look at here and you say, okay, where the x is right here, I have a 2x plus 3. So where the x is here, I put a 2x plus 3. So this would be 1 over 2x plus 3. But then we go back to this previous rule that said whenever you have a number multiplied inside times the x, you have to kick it out. So you would have to times by a 2 because of that 2 right there. Plus 3 doesn't do anything to it. And so there would be your derivative right there. Okay? So that's what that would look like. That's how you use the rule. All right, now, what if you have logs of another base? Now, this doesn't happen very often, so it's one of the reasons we miss it, because we don't see it very often. We forget about it. The ones we use all the time, we tend to get pretty easily. But what if you had log of a different base? Well, it's kind of like an exponential. It's basically the same thing. It's still 1 over x, but then we have to tack on, and instead of ln b, we tack on 1 over ln b. We tack on a 1 over ln b. Okay? All right. So, there's exponentials and log rules for derivatives. When we have one of those functions, we apply it. And then, of course, if they shift or we have a number on the inside or whatever, we compensate for that. All right. That's section 2.6 in a nutshell, the new parts of that. Now, what we do with it and how we do max-min problems and all that, then that gets to be some more stuff. So that's some of what we'll be working on over the next couple of days. Today's homework is mostly about just using these derivative rules and getting used to it. All right. 2.7 is about the trig functions. Think about it now. We've already done power rules, so like polynomial type functions we can handle. Now we've done logs and exponentials, and now we're going to do the trig functions. And that should give us a really good understanding, or it should give us rules for all the different types of functions we can run into. And then chapter 3 gets into all kinds of weird combinations of those and how we have to deal with those. So the first one, of course, we already have, sine x. We know the derivative of sine is cosine. And like we said, if there's a 2 on the inside or something like that, we use those other rules we talked about to deal with that. All right. Now, what about the derivative of cosine? Well, turns out, now remember how we did the derivative of sine. Remember that? We plotted a bunch of slopes. We looked at some slopes. We did a graph of them, and it was that aha moment. Everybody went crazy. And it was a cosine graph. Well, it turns out the derivative of cosine is negative sine. Negative sine. Okay? That's the derivative of cosine. So these are just to be memorized, quite honestly. That's what we're going to have to work on. All right. Now there's 6 of them, remember. There's 6 trig functions. We're going to do all of them here now. So now let's do the derivative of tangent. The derivative of tangent is secant squared. Now remember, that really means secant of x all squared is what that really means. The derivative of tangent is secant squared. Okay? Don't really know why at this point. We'll learn it later in chapter 3 why it is, but you don't really need to know that, to be honest with you. It just memorize, that's what it is. All right, and then finally, finally on this page, let's do cotangent x. Derivative of cotangent. Now you'll start to see a little bit of a pattern that's going to help you memorize it. The derivative of sine is cosine. The derivative of cosine is negative sine. The derivative of tangent is secant squared. The derivative of cotangent is negative cosecant squared. So if you can memorize tangent, you can get cotangent pretty easily. The co-functions are all negative. The derivative of cosine is negative sine. The derivative of cotangent is negative cosecant squared. And then we'll see the last couple here right now. So the derivative of secant x is secant x tangent x. Now notice, it wouldn't be a bad idea at this point to get used to writing x's and parentheses around those x's when you do these trig functions. Because in trig we get real lazy, right? You just secant tangent and we don't write the x and we don't put parentheses around the x. That can really get you into trouble here when we're doing derivatives because we talk about the inside of the function. Well, it's what's in the parentheses. If you're not writing parentheses, it's hard to understand it. Yes?
So do we have to memorize all those ones before these two?
Well, I'm not going to give you a quiz on these rules. In other words, you're not going to have to write down those rules. You're going to have to use all of these rules. You're going to have to be able to use them all, right? So, like these especially. I mean, you're just going to have to know that when you have a number out in front of a function, it just stays out in front, right? You're not going to have to memorize that, right? That. So what?
So yes.
So the answer to your question, I wasn't quite sure, but yes, you got to know them all. Absolutely. You got to know these all. Okay? Derivative of cosecant, take a guess what it is. Negative. What do you think? No. Cosecant, cotangent. All right, remember the derivative of tangent was secant squared. The derivative of cotangent was negative cosecant squared. The derivative of secant is secant tangent. The derivative of cosecant is negative cosecant cotangent. Okay? Yeah, so to be honest, memorizing most of them is not going to be that much of a problem because we're going to use them so often. There will be a few that we don't see very often that you will have to work a little harder to memorize because you just don't see them very often. Now, when we do a test, a quiz, over this stuff, to be after Thanksgiving. Now, we're going to take a quiz next Tuesday. You're going to have to know kind of these basic rules that we've just talked about here. Now, we're going to be adding to that list when we get to chapter 3. And so after Thanksgiving, when we take our quiz on derivatives, on all types of derivatives, right? Be the week after Thanksgiving, maybe a week and a half after Thanksgiving, whatever. It's called the gateway test. And the gateway test for derivatives, what it is you have 10 functions. You have to do the derivative of those 10 functions. And you have to get 8 out of 10 right. And you have to keep taking a version of that until you get 8 out of 10 right. The longer it takes you to get 8 out of 10 right, the lower your grade. So if you get 8 out of 10 right the first time, you get 100%. So you get 8, 9, or 10 right, you get 100% quiz grade in the book. Then you have a few days to try a couple more. You have to come in on your own after that. Okay? And if you pass the next couple, you get 27 out of 30, which is still an A. Okay? And then you get a couple tries after that. And then you get a couple tries after that. And then we're pretty much to Christmas. So hopefully by then you've had a chance to take 5 or 6 or so. And you should hopefully have passed it by then. But that's down the road. Well, yeah, at some point the grade goes down because it's based on how much time it takes. I guess it's a 0. Well, actually, I let you do this. At some point, I let you take whatever grade you have. So, for example, if you can't get to 8 out of 10, and at some point your best was 5 out of 10, well, you can take a 50%. You can take a 15 out of 50. But after a couple weeks, your grade has went down to that's the best you could get anyway. So it doesn't matter if you get 8 out of 10, right? Hopefully, we don't have anybody in that boat. To be in that boat, you pretty much have to not try. You pretty much have to not study and just not even try. And then, that's pretty much what has to happen. Okay, I want to show you a problem here. This is the 2012 AP test. I think I had this up the other day. This is the actual AP test. That's right, because somebody yelled at me and told me to go grab this over here. All right, let me see if I can find a problem I'm thinking of. Be on the lookout for it. It's got limits in it. Oh, you know what's in the no calculator? I do know that. It's got limits and tangents in it. And I saw it the other day. Oh! Nope, here it is right here. No, it doesn't have tangents in it. That must have been on a different thing. All right, here is a problem on the 2012 AP test that was this is a no calculator problem, okay? Does this look familiar? All right, this better look familiar, okay? What is it? The definition of the derivative. Now, we did pretty good there, but now think about it January or February when we're doing our midterm, and we have not done a definition of derivative since November, what is today? 19. Okay? Now we may not be as good at recognizing that as definition of the derivative. This is a definition of the derivative. Now remember that worksheet that we did where we had to look at something like this and we had to tell what the function was. Remember that? Just a few days ago. Well, what was this function? ln of x. Because the 4 plus h must be in here where the x was. And so, since this means derivative, this limit means a derivative at what? 4. So what they're wanting is f prime of 4. So when people see this, they think it's a limit problem. So people will see this. When we get to that point, you'll try to do algebra. You'll try to distribute an ln, which is a horrible thing because you can't do that. And then you'll try all kinds of weird stuff. You say, oh, God, I hate limits. I hate limits. This isn't a limit problem. It's a derivative problem. It's a recognize that that's a definition of derivative. You recognize the function's ln x. What is the derivative of ln x? We just learned it. 1 over x. And so if the derivative of ln x is 1 over x, and now we want to plug a 4 in, the answer to this is 1/4. It is not a limit problem. It's so remember I said they like to quiz you on several things at once? So what they just did there is saw if you understood what the definition of derivative was, and they also saw, do you know the derivative rule for natural log x? And then you plug in your 4, and there's your answer. Okay, so that would combine those kind of things on some of the stuff we've learned. All right, let's do a couple of example problems here. Let me see. Let me pull one out here. And then the last thing we're going to talk about is antiderivatives of these things a little bit, just real quick, and then I'll let you have some work time. All right, so let's say we had a function that was sine 3x minus 2 to the 4x plus log base 3 of x minus 7, and let's put a 4 in front of that log. Let's put a 4 in front of that log. Okay? Find f prime of x. Okay? Write it down. Write it down. Write down the derivative of that function. All right, I'm going to put it up here. Look if you want.
Now we'll talk about rearranging and rewriting and those kind of things. But let's just, any questions about what you see here? Yes, Al? Why is the natural log of 2 there? And then times 4. They're from two different things, right? So here's the thought process. So in this one, we're all good with that, right? We kick out the 3. We talk about the kicking out when you have a number on the inside with the x. Well, that's what we have here. This 4 is a number on the inside, right? The inside of this function, there's not parentheses there. I could put it, but typically we don't because it doesn't, mix up with anything else there, so we don't have to. But the parentheses here, I think, are more important. If I don't have the parentheses here, then we think the log is just the x, not the -7, so we kind of need the parentheses. So that's the inside. So we're using 2 rules here. One rule is this rule, right? The rule that's 2 to the x. The derivative is 2 to the x and then times the ln2, right? So that's where the ln2 comes from. And then the 4 comes from this rule. There's a 4 on the inside times the x, so we have to kick out the 4. So it's 2 rules put together. So and then also the rule that says when you have an exponential, it's its own derivative, right? B to the x, the derivative is b to the x, and then tack on that ln b. So the derivative of that is itself, the ln of the 2, and then the 4 comes from there, right? So it's combining those 2 rules. It is not bringing this power down in front, right? That is not what we do. That's not a power rule because that's not a power function. That's an exponential function when the x is up in the exponent. Okay, so it's a different function, different rule. All right, the log rule, the 4 just hangs out. The log rule is 1 over x. That's the log rule. So we do 1 over x minus 7. But then other base of logs, we have to tack on the 1 over ln b. And that comes from this rule right here, right? That rule right there. So the rule is 1 over x and then 1 over ln b, which in this case was a 3. So 1 over ln 3. Now, it would be perfectly fine to leave that answer that way. Where people get in trouble is sometimes they think they can bring this 4 in with that 2 and make an 8, and you can't do that. Okay? So it's perfectly fine to just leave that like that. This one, we could put that together, maybe put the 4 on top. Then we would probably need to make sure we put parentheses around that x minus 7. You'll be amazed when it comes time for that gateway test that we talked about where you got to get 8 out of 10 right. Having missing parentheses, leaving them off, causes more people to miss probably than not knowing the derivative problems. If you would write x minus 7 and then ln 3 on that bottom, you would miss it on the gateway test. Because what you've put, when you write it like this, you've attached the 7 to the ln 3 but not the x. The parentheses being there versus not being there mean 2 different things. And you know what some people do? Is they'll put a time sign right there. And sometimes to really emphasize it, they'll put a great big time sign. Right? So that looks like, so what they're thinking is, see, I got the x minus 7 over there, and then I got the ln 3 there, and they're times. No, that's not what that means. Order of operations says multiplication takes precedent over subtraction. So no matter how big you make that time sign, only the 7 is attached when you write it that way. So this would be wrong. Yes.
Do we have to write it like that?
You don't. If you left it like this, that would be fine. Yep. If you left that last part like that, that would be fine. Okay? All right. So you're going to get some practice with ones like that. Let's do one other quick one, and then I want to talk about an antiderivative real quick. So f of x, because we didn't put any of those on the last quiz because we had so many other things going on. So on this quiz, there will be some of that. So I just want to do a real quick one here. Let's say we had tangent of 4x plus oh shoot, let's do x to the e minus ln 3. Do f prime of x.
Ready? Oh. Now at the end there, I've put a couple of functions in there that you rarely ever run into, but they really make you think about the rules. How about the first one? Are we okay on the first one? That was pretty easy, right? Derivative of tangent x is secant squared x. When you have some on the inside, you leave it in there, but you also have to kick out the 4, right? So that's a secant squared problem. Okay, how about this one? Good with that? That's good, because I usually trick people with that one, right? That's a power rule, because it's x raised to a number. E is just a number. Now, e to the x is a function. It's got an x in it, but e itself is just a number. So x raised to the e is a power rule. Bring the e down, drop the power by 1. So that's a power rule. How many had a minus 1/3 at the end? Gotcha. The derivative of the function ln x is 1 over x. What's ln 3? Type out. ln 3 is a number. It's like having a minus 7 at the end. What's the derivative if you have a minus 7 at the end? 0. The derivative of ln 3 is 0 because it is a number. It is a constant. Okay, but I tricked you. That wasn't fair. But I wasn't grading you on it either. So, okay. The next quiz, though, that might be on there, right? That could show up. If it said ln of 3x, that's a different deal because that's a function, not a constant. It's a changing thing when it has an x in it. All right, now, here's another one that gets people sometimes, what I do, I think, is along those same lines, what if I would have had ln 3 times x and said, now do the derivative of that? Then it would be what? It would be ln 3. Because what is that? That's like, that's asking what's the derivative of 7x? What's the derivative of 7x? 7, right? Can't believe it. The derivative of 7x is 7, right? It's just a number in front. This is a number times x. You bring, it'd be a power rule, bring the 1 down in front, drop to a 0, whatever, it's just ln 3, right? So again, ln 3, just a number, treat it like a number. And that's, I'll be honest, when I'm doing those problems, that's what I do. When I see ln 3, I say, oh, that's like a 7. And then I just do the problem with a 7 there instead, and then substitute it back. All right, one last one here, and let's do this now. Now remember, antiderivative is simply doing a derivative in reverse. Now that we've got these derivative rules, we can think of backwards, but the most important part of this is actually the check. The way you do an antiderivative is you kind of guess and check. You say, well, I think the rule backwards would make it be this, but I don't know. Let me do the derivative of that and see if it gets me back to the red. So the blue, your answer for the blue, you have to be able to do the derivative and get back and give you the red. Okay, see what you come up with. This is pretty tough first time around. All right, if you really think you're onto something, don't look up here because I'm going to put it up here in a second, okay? Just because I want to give you some work time and I want to get you started on the first couple of problems so you see what's going on, okay? But and maybe that'll leave you some work time, but at least I give you a running start on the homework, okay? So here it is if you want to see it. Now, yeah. Now, the way to look at yours is, and again, I'm not kidding when I say an antiderivative is really kind of a guess and check. It really is. And even when we really learn after Christmas and really focus on antiderivatives, it'll still kind of be a guess and check. Now, we'll get better at it as we go to where we have more of an idea, but it's still kind of a guess and check. All right? And you always, the check is the key part of that. The check is do the derivative. Now, let's just check my answer to see if this wouldn't be true. So first of all, where'd my negative come from? Well, I knew the derivative, I knew sine and cosine go together with derivatives. So I tried cosine, and when I do the derivative of cosine, I get negative sine. I'm like, oh, well, I don't want negative sine, I want positive sine. So there must have been a negative here. Remember, that's just a number that hangs out in front. So I must have had a negative out here, so I do the derivative of cosine, I get negative sine, that cancels that negative, makes it positive. Also, when I do the derivative of cosine 2x, what do I do with that 2? I have to kick out a 2, but there's no 2 kicked out here. So therefore, I'm going to need a 1/2 out in front, so when that 2 kicks out, it'll cancel. You see how that check part goes? So you try what you think it would be, because we know the 2x is on the inside, then that has to stay at 2x on the inside. So we try it, we do the derivative, you say, oh, oops, there should be a 2 there. Well, there must have been a 1/2 there that made it go away. That's what I was doing. And the same thing is true here. 2 to the 5x, I know it's its own derivative. So I know I must add a 2 to the 5x. However, when I do 2 to the 5x derivative, now remember, these are just numbers here. So what do numbers on the outside do? They just, no. Numbers multiplied on the outside, 3 times sine x, what's the 3 do? It just hangs out there, right? A number multiplied on the outside. Rule number 2, a number multiplied on the outside just hangs out there. So these numbers here, I know are just going to hang out there. So 2 to the 5x, the derivative will be 2 to the 5x. This goes back to Allie's question earlier. The rule says we have to tack on an ln2, and the other rule says when you got a 5 on the inside, we got to kick that out. So if I do the derivative of that, I know it's going to be that. Well, I don't have that. Those things aren't there. So what's that mean? That means there must have been something there that made them go away. So the 1/5 and the 1 over ln2 are there to make that and that go away. That's where those came from. There's no rule for antiderivative. It's simply the derivatives in reverse, and when you check by doing the derivatives, you get those. Now, I've given you one right there that's harder than most that I would even give you on this next quiz. There might be one that's got a part that's kind of like that, but I just wanted to get the point across right here. All right, so your homework is going to be in sections 6 and 7. It's going to be this first line on your assignment sheet. The next grouping below the solving equation worksheet. Okay? So, there's some out of section 6, which is the exponential and log section. And there's some out of section 7, which is the trig section. Now, I guess there won't be a lot of work time. Actually, what we're going to do is I'm just going to work some with you. So that'll be your work time and it'll get you started on it. Now, okay, section 6 is the exponential log, and section 7 is the trig. All right, so if we look at problem number 6. Oh, and keep in mind, right, that f prime is the derivative, f double prime is the second derivative, which means you just do the derivative of the derivative, right? So if you have to do a second derivative of a function, you do the first derivative, and then you do the rule again with the next derivative, because that is some of what you have to do on those problems. Okay, so number 6 says let h of x equal log base 10
of x. They want you to find h prime of 1. Was it 1? Is that the first one? Or is it 1/10? No, it's 1/10 actually first, isn't it? Yeah. H prime of 1/10, h prime of 1, h prime of 10, and h prime of 100, I believe. Okay, well, we're doing shortcuts now. We're doing these rules. So how do we find h prime of 10? Well, first we have to find h prime of x. That's right. So what we need is to do the derivative of log of x, log base 10 of x. And what is that derivative? 1 over x times 1 over ln 10. Once you have that, now the rest is easy. So we put a 1/10 in for x. What's 1 over 1/10? That would be 10 times 1 over ln 10. Right? Now, could you put that as 10 over ln 10? Sure. Right? H prime of 1. Put a 1 in for x. That's just 1 times 1 over ln 10, or just 1 over ln 10. Just leave it like that. That's fine. No. No, it's not ln of 1. H prime of 1 means we put a 1 in for the x. Right there. Yeah, we're just putting the 1 in there for the x. This is just stays there. That's just a number. H prime of 10. We put a 10 in for x. So that's 1/10 times 1 over ln 10. You see what I mean? Now, the problem said use theorem 12. Well, that's just what your book called the log rule. Right? We wrote down our rules, a list of rules. In the book, they call them theorems. They do a certain theorem. So if you see use theorem this or use theorem that, just ignore it. They're just saying use the derivative rules, is all they're saying. Okay, so that's it. So you're going to get into some where they're going to give you a function. You're going to do just like what we were practicing. You're going to do f prime, f double prime. All right, now let's turn to section 2.7. And we'll get started with number 10 on your homework here. Now this is the trig section. Now this is where you're going to get into a little more chart kind of stuff. All right, you're going to get into some chart kind of questions here, more so than in section 6. And that's because exponentials and log graphs are pretty boring. An exponential graph just kind of goes like that. It's always increasing. It's always concave up. There's no stationary points. There's no local max or min. I mean, there's not much to do on the chart when it comes to an exponential or log function. So we don't do much in that section with it. But trig, there's tons of them. There's maxes and mins all over the place, inflection points, all that stuff. So we'll be doing those more with trig functions. This is the time now where you're going to have to be able to do trig stuff without a calculator, unit circle, that kind of stuff. This next quiz, there will probably be a problem. Remember on this last quiz, we had a problem with local max and increasing, decreasing, doing a number line. This next quiz, almost promise you, there's going to be a problem just like that. It says to be a trig function, not just a polynomial function. So here's an example right here, number 10. So, number 10 asks, where is this function? Stationary points, inflection points, local max, local min. That's 10 through 13. So, here we go. To find stationary points, we do the derivative. And what would be that derivative? 1 plus cosine x, and we'll set it equal to 0. Right? Just like we've been doing in this other section like we did for today's quiz. And now we're going to solve that. So you can see why we did the review sheet with solving equations today. So we're going to solve that. This would be a no calculator problem. Okay? I think the directions you can say, no, they don't work, but just assume it's no calculator. So where does cosine equal -1? Now, we do have to be careful and realize that our interval is from -5 to 5. So it would also be -pi. Now, how are you going to get that? Well, you take a unit circle. Negative 5 to 5 would almost be like negative 2 pi to 2 pi almost, right? And over here, if you go this way, that's pi. But you could also go back this way, and that'd be negative pi. Now, another way to think about it is just think about the cosine graph. Here's the cosine graph. Where does it equal negative 1? Right there and right there. Pi and negative pi. Okay? If you look at the cosine graph between negative 5 and 5. Okay? So we've got those two are stationary points. So what do we do with those? We put those on a number line. Right? So there's nothing new here except doing the derivative of sine, which we actually already knew that one as well. Otherwise, there's nothing new here when it comes to local max, local min, and stuff. Now, a couple things different when you're dealing with a trig function. When we go to do our number line, now in between here, 0. Of course, there's going to be an obvious one to put in. But what's a number less than negative pi? Negative what? Well, yes, but I guess here's what I'm saying. Where are we going to plug these blue numbers into? Into the G prime. Do we really want to plug a 5 into cosine and do cosine 5? We'd rather do pi type numbers. So negative 2 pi would be better. Okay? Now that's outside the interval, so that gets a little bit interesting, but we'll go ahead and do it. That's fine. And then we'll do 2 pi. Now sometimes that can get us in trouble, and we'll find out when that happens. Okay, so now let's put negative 2 pi in here. What's cosine of negative 2 pi? That would be all the way back around to positive 1, right? So 1 plus positive 1 would be positive. Put a 0. What's cosine of 0? That's also positive 1. What's 2 pi? Okay, something's going wrong. Well, not really. Well, what would this mean? Well, maybe that's right. Maybe that's right. What does that mean? Those are all what? Flat spots. Okay, let me check real quick. Oh, duh. Jeez. 1 plus cosine. Think about the cosine graph. And think if you shifted it up 1. Shift it up 1. Does it ever cross? It'll just touch, but it'll never cross. It'll be positive all the time. So the graph's always increasing except those places where it's flat. Okay. Well, I mean, it reminds me of the other time I thought it was wrong. And turned out it was. All right. Okay. So that's your homework. The one other time, right? Well, that's the only time I've been wrong. Is the times I thought I was wrong and turned out I was right. So. Right, Mr. Martin?
You say you've been wrong.
Yeah.
Your head's
It-
been bored.
I was wrong the times when I thought I was wrong and it turned out I was right. So it was wrong of me to think that I was wrong. See, that's when I. You would think I'd learn, but no.
Yes.
See, when I act like that, then they understand my children. All right. Kind of picked on Ryan today, so you might.